Okay, in this podcast we're going to take a look at how we actually calculate the equilibrium constant K, Kc or Kp, and we're going to learn how to use what's known as an ICE table to help us organize our information in order to determine what the K is. Okay. So first of all, let's talk about the equilibrium expression a little bit. So here I'm going from 2NO2 to N2O4. They're both in the gaseous state, so I could calculate Kc or calculate Kp. But since I'm given concentrations and it's information on Kc, I'm going to focus on Kc. Now, one of the things we need to understand is that at different temperatures, my K will differ. So when I'm talking about Kc or Kp or any K, I need to specify what temperature I'm talking about because it will change. But at any given temperature, it does not matter how much reactant or product I start with. I could start with all reactant and no product, all product and no reactant, half and half, or some other quantity. But in the end, I am always going to end up with the same Kc. So my equilibrium constant is going to be the same. Now my final, at equilibrium, reactants and products concentrations are going to be different. But Kc, the ratio of the products over reactants, is always going to be the same. In this case, about 21. Okay, so let's take a look at what an ICE table is. Some people will call this a RICE table because the first thing we show is the balanced reaction. But most people call it ICE, and that's because the first row in that table is going to be the initial concentration of our reactants and products. C is going to represent the change during the reaction of the reactants and products, and E is the equilibrium concentration of reactants and products. Alright, so let's go ahead and try one. So here we're told we have this reaction between SO2 and oxygen to give us 2SO3. And the equation's already balanced, and it says if the initial concentration of SO2 and O2 are 0.1 molar, and the equilibrium concentration of O2 is 0.75 molar, what is the value of Kc? So let's go ahead and fill out the table with what we know. So the first thing we're told is that SO2 and O2 start with a concentration of 0.100 molar, 0.100 molar, and that the equilibrium concentration of O2 is 0.075 molar, 0.075 molar. Okay, so let's see what else we might be able to just figure out. So if we're starting with product, we can assume that our initial concentration of we're starting with reactants, we can assume our initial concentration of product is 0. None has been made yet. Now we can also say that as the reaction moves in the right-hand direction, that I'm going to lose some amount of oxygen and some amount of SO2 and gain some amount of SO3. And I can also say for every mole of O2 I lose, I'm going to lose 2 moles of SO2 and gain 2 moles of SO3. So the way I put that in my table is going to say I'm going to lose some amount known as X of O2. I'm going to also lose some amount of SO2, but it's going to be twice as much based on the coefficient in the balanced equation of SO2. And I'm going to gain some amount of SO3 that is plus 2x, right? Because the balanced equation, its coefficient is 2. Now I can go ahead and write my equilibrium amounts based on what I'm starting with. So I'm going to start with 0.100 molar minus 2x. I already know the equilibrium concentration of O2, but for SO3, my equilibrium concentration is going to be 0, is what I started with, plus 2x, so it's going to be simply 2x. Okay, so in order to write my equilibrium expression, I have to know my concentrations at equilibrium. So in order to do that, I have to figure out what X is, and I need to look at my table and see if there's any way I can figure that out. Now, in fact, there is a way because I have an equality here that I can use. So my equilibrium concentration of oxygen is going to be equal to whatever I started with minus what change occurred. So my 0.100 is what I started with, molar, minus X is going to equal 0.075 molar. And so if I solve for X, I'm going to get X is equal to 0.025 molar. Now I can plug this in for my X in my equilibrium expression, right here, my equilibrium concentrations. And when I do that, I get the table on the next slide. This is what I end up with. So I've changed this, I've replaced the X, and calculated what my concentrations are going to be. Okay, so if I take that now, and I write my equilibrium expression, or my law of mass action, I have SO3 raised to the 2 power over my reactants raised to their coefficients. Okay, and if I plug in those amounts, which are the equilibrium amounts, I have SO3 right here, I have SO2 here raised to its coefficient, and I have O2 here. And if I plug these in and I calculate, I get my K is going to be equal to 13.3. Okay, so here we have a problem. We have an initial concentration of 1 atmosphere of NH3, and it reacts according to this balance equation. At equilibrium, the pressure of NH3 is 0.8 atmosphere, and we want to know the initial pressures of nitrogen and hydrogen. Okay, so let's go ahead and figure out what the initial pressures are going to be. So what I'm told is I'm starting with 1.00 atm of NH3. And if I'm starting with 1.00 atm of NH3, what are my initial concentrations of N2 and H2 going to be? So take a minute and answer that question, and we'll come back to it. Okay, so if I look at my balance equation, I have 2NH3 become an N2 and 3H2. There's no mention of the initial concentrations of my products N2 and H2, so I'm going to assume I'm starting with all NH3, and I have 0 N2 and H2. Okay, so the answer is going to be A. Alright, so what is the change for each of the 3 species in terms of X? So here I'm going to use the coefficients in my balanced equation again to figure out how many X's I have. So if I'm starting with 2NH3, my assumption is I'm going to lose some amount that's minus 2X, and I'm going to gain product. So I'm going to gain X for N2 because its coefficient is 1, and I'm going to gain 3X for hydrogen because its coefficient is 3X. So I'm hoping you got your answer of B. Okay, so what is the value of X? Well, we can calculate that based on what we have here, where we know that we are starting with 1 atmosphere of ammonia, and that we end up with 0.8. So we can set the equality 1.00 atmospheres minus 2x gives me 0.8. If I solve for x, I get 0.10. Okay. So if I end up with x of 0.10, what are the final pressures of N2 and H2 going to be? So go ahead and answer the question and then come back. Okay. All right, so this 0.0 is the pressure of the NH3, and what we determined in the last slide is x is equal to 0.10 atmospheres. So if I go from 0 to plus x, I'm going to end up at 0.10, 1, 0 here for N2, and I'm going to end up with 0 plus 3x, and x is 0.1, so I'm going to end up with 0.30 atmospheres of H2. So my answer would have been A. Okay, now that I have my equilibrium concentrations of my reactants and products, I can write my equilibrium expression. So the Kp is going to equal the pressure of my products of N2, right, and the pressure of H2, and I have to raise that to its coefficient, which is 3, over my pressure of NH3, and that is going to be squared because of the coefficient. And so once I've done that, let's see if we can figure out the value of the Kp. Okay, so what is my Kp going to be? So go ahead and see if you can solve this, and then come back and we'll plug in the values. Okay, so I had the pressure of N2, and that was 0.10, and the pressure of H2, which was 0.3, and that was raised to the third because that's its coefficient in the balanced equation, over the pressure of NH3, which was 0.8, and that is squared because it's got a 2 in the coefficient, and this is going to be my Kp. So if I plug all that in, and I end up with a Kp of 0.0042. Now, the K is much less than 1, so take a second and determine what that tells us about whether the reactants or products are more favored. Okay, so it does tell us that the reactants are favored because my K is much less than 1, and when my K is much less than 1, the reaction is favors going in the left direction. Remember, if K is much greater than 1, that means products are favored. Okay, so we're going to stop there.